Okay, so here we have a pretty standard problem. An object is placed 25 centimeters in front of a concave mirror with a radius of curvature of 20 centimeters. All right, so we need to first of all find where the image will be located and determine if it's real or virtual, and then find its magnification. So from the last video, we had learned that, slide this up, oops, 1 over dO plus 1 over dI is equal to 1 over F. And we also know that the magnification is negative dI over dO. So those were the mirror equations we had found in the last video. All right, so there are a lot of things to keep track of here. And we can see that we have not been given the focal length of this mirror. But remember from a previous video that the focal length is exactly 1/2 of the radius. This shows up several times in the homework problems. So when you're working with mirrors, they often give you the radius of curvature, but they're indirectly giving you the focal length. So let's list out what we know. All right, we need to, well, first of all, let's list out our variables in this problem. dO, dI, F, are the main things, and then we can find M once we know those. All right, so if the object is placed 25 centimeters in front of a concave mirror, that means the object length is 25 centimeters. The image length is something we don't know. All right, the focal length is going to be 20 centimeters, but divided by 2. It's half the radius of curvature, so that makes it 10 centimeters. All right, and the magnification we don't yet know. Okay, so there are two things we don't know, but we have two independent equations to work with. We've already used the third equation, that F equals R over 2. So we have two equations left that we can substitute in. We can see that finding the magnification would be difficult to do if we don't know dI. So if we don't know dI and we try to find M, we can't do it directly, right? But we can use the first equation right away to figure out what dI is. So let me do that right here. So 1 over 25 centimeters plus 1 over the unknown dI needs to equal 1 over the focal length, 10 centimeters. All right. So now we probably want to get a common denominator here. Well, let's actually, we're going to be solving for dI. So 1 over dI is equal to 1/10. Oops, erase that, minus 1/25. This is all much nicer if we get a common denominator. So 1 over dI. When the numbers are nice like this, you may want to get a common denominator. When the numbers aren't nice, just do the subtraction in your calculator, and then we'll take the reciprocal in the last step. But these numbers are nice. So we have a common denominator of 50. This is 5/50ths minus 2/50ths. So this ends up equaling 3/50ths. So if I want to find dI, it's the reciprocal of that, 50 over 3. And if you divide 50 by 3, let's see what you get. You have 10, it's not quite 20. Okay, so we have, I'm just trying to do this quickly in my head. I think 13, 3 times that. Oh my goodness, it is late. So it's not quite 17. It's 16 and 2/3. All right, so there's that, or we could say that's 16.7. All right, so yes, that will work out. So that's approximately 16.7 centimeters. Okay, so that's where the image will show up. Now notice that was a positive 16.7. So what that corresponds to, if we look back at one of these pictures, if dI is positive, it does in fact mean that the image forms on the same side of the mirror as the object, and it is real. Okay, so the question said, is it real or virtual? When dI is positive, we can say this is real because dI is greater than 0. Okay, So we know when we get positive answers for image lengths that we're looking at real images. Okay, so we have that taken care of, and now it's pretty easy to find the magnification. It's just negative of di over do. So di we just found to be 16.7 over do, which was, let's see, that was 25. We might actually want to go back to the fraction. So it's negative 50 thirds over 25, and we can 50 thirds times, instead of that, we can say 1/25. Oh, and that very nice negative 2 thirds. Okay, so when I do that, I can look at the magnification, and so let's figure out what this means. The negative means it is inverted. Two-thirds is less than 1, so it is smaller. Okay, so notice our starting distance was 25 centimeters and the focal length was only 10 centimeters. So we're pretty far outside of the focal length. And like we had talked about in our ray tracing video, that means we're going to get a small, real inverted image. And that's exactly what this math shows. Let's do another one. Okay, so this time we want to solve for the radius of curvature of a mirror. If we have an object 20 centimeters away and we have an inverted image, oh, I should have said the image is inverted, and multiplied by a factor of 2. Okay, so let's just scratch this. Let me just write the problem so I don't have to start the video over again. I'll say, what is the radius of curvature of a mirror if an object that is 20 centimeters away creates an inverted image. That's what I left out. An inverted image that is twice as large. Okay, so there's some clues in here. Okay, we know this is an inverted image, so we have a negative magnification. We know that it will be a magnification of -2, all right? We know that it's 20 centimeters away from the mirror, so we know that DO is 20, all right? But we don't know DI, and we don't know, let's see, we don't know F. All right, so we have 2 things that we don't know out of this list, but fortunately, we have 2 equations, right? So let's start with the magnification equation this time, since we know the magnification. We know that M is negative DI over DO. So we can fill in -2 is equal to negative. We don't know DI, but we do know that DO is 20 centimeters. I should put units on there. So this is pretty easy to figure out. DI must be 40 centimeters. Okay, so in this problem, we were first able to use the magnification to figure out DI. Now we haven't answered anything about the radius of curvature of the mirror. We need to go to the other mirror equation. And remember, if we can find the focal length, we can just double that to get the radius of curvature. So now we know DO is 20 centimeters plus DI is 40 centimeters, so 1 over 40 centimeters. That must equal 1 over the focal length. Okay, so let's add these fractions. If we think of the first one as 2/40, we have a total of 3 over 40 centimeters is equal to F. So, I'm sorry, is 1 over F. Therefore, F is equal to 40 centimeters over 3. All right. And then we can double that to find R. R is twice F. So we'll double it before we make it into a decimal. So it's 80 over 3. And if you take 80 over 3, I believe that's 20, 60, 20, 26.7. All right. So if you triple 26.7, I believe you get 80. So we have a radius of curvature of 26.7. The focal length was only half of that, 13.3 centimeters, but the radius of curvature will be 26.7. So that's how you do a problem where you've been given the magnification instead. Okay, so this time we'll have an object placed 10 centimeters in front of a mirror with a radius of curvature of 40 centimeters. So what we have not yet, oh, by the way, I better say a concave mirror. I'm not sure that I had that in the last one because we're going to do convex mirrors later, and we get very different answers because they're a very different kind of mirror. So this is much more like the first problem, except that we're going to be inside of the focal point. And we know from our ray tracing that when we're inside of the focal point, we get very different results. In fact, let me see if I have that. I don't know that I have it here. Let's see. Yes, we do. Okay, it would correspond to this picture right here. Okay, and we can see that when the object starts inside of the focal point, we should get a virtual upright large image. Okay, so that was the ray tracing that would roughly correspond to this problem. So now let's solve the problem and see what happens mathematically. Okay, so we want to start out with the mirror equation. And we want to fill in what DO, DI, and FR if we know what they are. Okay, so DO, we're 10 centimeters from the mirror. We don't know what DI is. That's what we're trying to find, the image location. And the focal length is 40 centimeters over 2, which is 20 centimeters. The key is that's bigger than 10. So we're looking at an object that is inside of the focal point, right? So now let's put in our numbers. When we put our numbers, I'll just start another column here. We have 1 over 10 plus 1 over DI is equal to 1 over 20. So let's see what happens. 1 over DI should equal 1 over 20 minus 1 over 10. So 1 over DI, hopefully you realize that's negative 1/20. Okay, 1/10 is 2/20. So if we subtract it, we end up with negative 1/20. So what is DI? DI is negative 20, and we put units on that of centimeters. Okay, now you'll notice in the previous 2 problems ago, when we solved for DI, let's see, right here, it came out to be a positive number, all right? And it was a real image. Now we get a negative answer, and it is a virtual image. Well, what does that mean? It means that it's on the opposite side of the mirror. Okay, so going down, we're looking at, whoops, I went too many cases up. It's right here. Okay, so instead of being on the side of the mirror where the light is actually reflecting, it's on the other side of the mirror. It could even be, there could be a wall back there. So it appears to be behind the mirror on the other side. So it's on the side opposite of where the light rays are incident and reflected. Okay, so that's what a virtual image looks like, and that's what a negative image length means. Okay, so the negative image length means we will have that image showing up on the opposite side of the mirror. Okay, so include that. I go with blue here. So the minus sign means image is 20 centimeters behind the mirror, and it is virtual. Okay, so a negative image length means you have a virtual image, all right? Then we're supposed to figure out what the magnification of this is. This is easy now, it's just negative di over do. So it's negative 20 over 10. And hopefully you can see that that is positive 2. Now, what does the positive mean? That means that it's actually upright. And the 2 means twice as large. Okay, so the algebra leads us to having a negative image length, which means it's virtual, and a positive magnification. The positive doesn't mean it's bigger, it means it is upright. The positive 2, the 2 means it's twice as large. Okay, if that had been positive 1/2, which it can't be in this case, but we will see that soon enough with convex mirrors, a positive 1/2 would mean that it's upright and half the size. A positive 2 means it's upright and twice the size. All right, so this corresponds pretty nicely to what we had seen in this picture right here when we did the ray tracing.